All right, so as you all can tell, I am not KMP. Uh, if you're wondering where he is, or if he didn't say, he's out at a conference. So I'm one of the TAs for the class, so I will be giving you all the lecture today. So what we're going through is it's kind of like an extension of last class. Last class you talked about, you got an initial view at the stack and the heap, and kind of like how things go into it. You found that objects like strings and things like arrays go into the heap as kind of like stored data, whereas you also have like primitive data types that are stored in the stack under the different frames, different method frames. When you call a new method, that gets added to the stack, and so we're kind of doing almost like an extension of that, except we're also adding in a few additional factors. We're going to be looking mostly at just simple loops. So we'll have an iterative loop, such as a for loop. And we're also going to be looking a bit at recursion and how both of those factor into the stack and heap. We'll also go briefly over the idea of scoping, but it's going to be a bit more like, it's going to be a preliminary look at that. So without further ado, we're going to go ahead and get into it. So if you, I'm also going to be using the lecture code fairly heavily. We're just going to be working through everything in the code, basically. I've tried to include, the snippets of the code up there. So if you're having issues getting it downloaded or getting it ready, you should be able to follow along. Also, since this is an extension of what you did last class, I'm going to go ahead and assume that you all remember how to do this kind of like early stuff. So I went ahead and I'm skipping down to line 9 of kind of like the setup. So then we don't have to like just purely go over stuff I believe you did last class. So yeah, if we go ahead and look at this, you can see that we have args, vals, values, and that's all in the heap. I didn't include args though because space issue. And sum being a primitive data type that it is set in the stack. So we're going to go ahead and move down to this for loop. So one of the things you'll notice here is, and one of the things you might have noticed throughout your assignment is that variables, when they're assigned in a loop, act a little bit differently than if you just assign them in a method. And so this has to do with the idea of scoping. And so if you kind of like look at the illustration up there, you can see that within the stack, we have this new, it's not necessarily a frame, and you shouldn't think of it as one, but it's more of a, for the purposes of just illustrating it, this is considered a new scope. And it's considered a subscope of the main scope. And so now you're going to be asking, what is a scope? And so in essence, what a scope is, it's the binding and association of a specific name to some sort of variable. So if you look, sum is kind of associated with 0. Values is associated with that spot in memory. And so, each scope has its own sort of association, sets its own associations with different variables. So, one of the things you'll also find is that different methods have their own scopes to them. And so that's why you can, assign things to the same variable names inside a different method. Or you can assign things to the same variable names in different methods as you can, in others. And so with a loop specifically, such as this, the loop is contained within the main frame. It's inside that main frame, so it's considered more a subscope of the main scope, the scope of the main frame. And so what this essentially means is, the subscope will have access to the values in the main scope, but the main scope will never have access to these values in the subscope. It's essentially a one-way relationship with this. And so I'm sure there's been a few questions on Piazza kind of like concerning this general idea, but this is kind of like more a specific view of how it works. Is there any like brief questions about scoping from this like early point of view? Also, if I don't see you, just like keep your hand up and I'll try to get to you. So, And so this is what it kind of like looks like in code. So this is not in your example. This is kind of something I added in, of course, because this would throw an error. So as you can see, this sum variable that we're accessing in line 12 has been set within the main frame and is associated with the main scope. The child scope within the for loop is now accessing that. However, if we try later to access the variable I, which gets assigned to this child scope, this child for loop scope, then we cannot access its value because the parent has no access to the children. All right, make sense? Cool. Okay, so let's start actually with that out of the way, let's actually start going through this loop and evaluating the, what is it actually doing in terms of the stack and the heap. So I'm going to break this down line by line. When I say the code, it's more of what the machine is processing at a specific time. It's, as you can see here, we're looking up towards when the initial condition of the for loop. This is the check that happens every single time it gets back to the top of the for loop, and this is the check that basically decides if the loop continues or if the loop terminates. And so here we can see that we're accessing the variable I from the subscope, and we're accessing values length, which is initially it's in the heap, but it's getting accessed through values, and so it's still being accessed from the parent scope. And as you can see, 0 is less than 4, so we continue on with the scope, or we continue on with the loop. So now that we're inside the loop, we can begin to the process of summing. And so the main idea of this entire program is we're taking this array of numbers and we're just adding it all together. So we're going through. As you can see, we're accessing parts of the parent scope through the child scope. Sum is set to 0, so it is 0. Values is a spot in the heap. And then we're accessing a specific index of values by using the I variable. So, fairly straightforward. We go ahead and then we can access upwards back to the parent scope and turn it back to 1. Okay. Now we increase I by 1. So we add 1 to 0. We add 1 to 0. And so now we have I is equal to 2, and we're back at the top of the loop for the next iteration, or the next check before to see if we continue or not. So like before, we're doing the same, general layout. We're seeing that we're evaluating it to 1. We're seeing values.length, and we're evaluating it to 4. We see that I is less than 4, so we continue onwards with the loop. And so most of the stuff is basically kind of like the same general flow. We're going to be accessing different variables that we have declared throughout the main frame, the main part of the stack, and we're going to be accessing them purely through the subscope. And so the subscope is what's basically processing everything right now. If we were to do something that's not in the example code and say put in int a is equal to 0, within the for loop, where do you guys think that would get put in the stack? Any thoughts? So if we declare a variable a inside the for loop, so can you see my cursor? No, you can't. So if we were to put a variable int a right underneath the expression sum plus equals to values, where would that be placed? And it's an integer value. Yes? Yeah, exactly. So because we're executing through this subscope, any variables we declare will be bound to it. So we would have an additional name, which is a, and it would be set to 0. And so that a value will not be accessible to anything later on in the code because it is because later on past the loop, none of the things that are declared or called in the loop will be used later. So that's why it's important that we have this sum integer, which is declared outside the loop, which is basically the variable that stores all the data that we're parsing through. It basically is how the loop communicates with the outside world. Okay. So again, continuing on with this basic loop, we go back down some. We increment it by the next value, which, as we saw on the previous slide, resolves to 7. So we increase 1 by 7, getting 8, and that gets updated in the main frame area. Any questions up to this point as well? Yes?
Will we need to know how to draw diagrams that sort of narrate this process, like with the stack and heap?
I don't believe so. If you want a more concrete answer, you can ask KMP. I think the diagrams are just more to help you visualize what's happening because it's a fairly abstract thing. So this is more for your benefit than something that you need to know how to do, if that makes sense. Any other questions? Yes?
Do you need to know the hexadecimal thing, under the value, or
So those numbers are kind of arbitrary. When a program is running, it will assign things wherever there's space to assign it. So you could run a program also multiple times, and you could end up having different different spots in memory being allocated to the same thing. So like if I create a string and I name it like a string and say it's like hello, and I run the program once, it might assign to like one spot in memory, and then if I run it again, it will assign to a different spot in memory potentially. It could also do the same spot. It's more of like wherever the compiler has room to put it. So the idea that you should know is that things such as so the basic idea that you should know is that memory is assigned and it's notated in hexadecimal. You don't really have to know anything specific regarding the numbers. I just kind of pick those randomly. Any other questions? Okay, cool. All right. So we're going back to the top of the loop again. We finished the bottom of the loop, so now we increment I again by 1, bringing it up to 2. And then again, we test our condition for continuing the loop. We see if I is less than the values.length. If it is, we continue. If it's not, we quit. And so as it is, we will continue once again into the loop. Again, much the same. We are taking the sum value. We are increasing it by 4 this time, as that's the associated spot in the array when the value is given I to index it. And so then we, of course, increment it back to 12. We do our test yet again, or we increase I yet again, bringing it up to 3 this time. And so one thing I think it's you can kind of see where this is heading. We'll eventually reach 4, in which case the test fails. But as we are doing this, we are moving through the entirety of the loop, or the entirety of the array, I'm sorry, through the loop. And so that's the main idea of using a for loop to access an array. So yeah, once again, we'll add 9 this time to 12, increase it to 21, and then we increase I again. So when we increase I again, this time we'll get 4. 4 is not less than 4. Therefore, the condition for the for loop to continue is now false, and so now the loop will end. So we have the scope that is part of the stack. It's no longer accessible, and so essentially what Java will do is you can garbage collect it, so it just disappears. So now we do the final print statement, and we get out 21 being our answer. Okay. One more round. Any questions of just kind of like how this iterative process works? Okay. Okay, so now we're going to talk about recursion. And so this is where things get slightly more complicated. So essentially what recursion is, it's when a method is calling itself. And so, how does it stop calling itself? Well, there's, like the for loop, there's a certain test condition that it needs to pass in order to stop calling itself. And so the loop that we'll be going through and is in lecture code example 2 is basically the same thing as the iterative way we just went over, except now we're doing it with recursion. So the test case is now we're waiting to see until we get to the end of the array, in which case we'll stop the recursion. And so that's and so you also have to take a sort of step when you're calling a method. You can't just keep passing it the same variables over and over again because that would never end. So there's certain, and so the test condition that stops recursion from happening is known as the base case. And the certain shrinking or the making it so that the problem is less big than you initially started with. It's basically making it more reasonable and continuing, making it so things are actually happening. That step's called the recursive step. I'm kind of keeping it a bit vague because this can take the form of a lot of different things when you're actually coding and in higher level classes. You'll see that recursion has a lot of capability in this regard. So here's kind of like a breakdown of the code and with all the things that I just mentioned. And so let's kind of think about why I label things as they are. So initial call, I think that's fairly straightforward. That's the first time I'm calling the method. We have the base case, which I labeled as position is equal to vals minus 1. And so the idea of this is we have, if you remember from just generally with arrays, the index starts at 0. So val minus 1 is equal to 3. So we're stopping when we get to an index of 3, which would be the last value in the array. And so how do we get there if we have if we're passing it a 0 for a position? So we're going to have to increase the position by 1 each time we call the method within itself. And so basically what this is doing is then making it so we're getting closer and closer to this sort of base case. We're getting close to being finished. So we'll start at 0, and we'll effectively be calling this method within itself 4 times, just so we can go through, or we'll be calling it inside itself 3 times, just so we can get to this base condition, and it can go through the entirety of the array. And of course, the recursion is the fact that we're even calling it inside itself. Any kind of questions about this? It's a bit, it's an interesting topic. Okay. All right. So yeah, we're going to break this down now with in regards to the stack and the heap. So if if there's any confusion about this explanation, we'll get to it hopefully. All right. So we have the stack, we have the heap. Back at line 9 where we were last time with all this general setup out of the way. So one thing we'll see here is that we can't actually complete line 9 because there's this method call within it, and we're expecting a value to be returned to it from it so that sum can be assigned. And so for right now, we're just going to do 2 dashes for sum, just to kind of signal that it's waiting on a value to fill it. It has its spot in memory, or it has a spot on the stack, and it's kind of in the process of being assigned, but we haven't actually assigned it to anything yet. We have to work towards assigning it. And so then, we add the method call onto the stack. And so when, the method call is made, it has, the integer vals, the integer array of vals, and the integer position in it. We are passing it, 0, so that gets set inside this method. And we're passing it the location of the memory in the heap. So then it has those 2 values that I can start to work from. And so, like I mentioned earlier in the lecture, this is a new method call. So this is a different scope from the main frame. This frame for the array from position, or array from pos, is a different scope entirely from the main frame scope. And so what does that actually mean? It means that they have no communication with one another in terms of the assigning of variables. The main scope can't access anything, any named variable set within the method, and the method can't access any variables that were set within the main frame. One way you could potentially work around this if you're coding something is to have a global variable which you set outside any frame. So you set it outside the main class and you set it outside the method call. I'll show you what this looks like towards the end of the lecture. I forgot to attach a picture to it here. So we'll do that after the presentation if we have time permitting. Anyway. Any kind of questions about how this works, the two different scopes? All right. Cool. All right. So I'm going to also add this arrow up here. This it's kind of it might be a bit hard to see if you're kind of further in the back. Basically, what this arrow is referring to is what is executing the lines of code, and this might not seem maybe necessary at first, but once you actually have these multiple, sections on the multiple frames on the stack from the additional method calls, it will start to become a bit more clear why this could be helpful. So right now we are executing code from the, this initial sum array from position. We are, testing our base case up first, as that's the way it's designed, and so we are seeing if the position value given to it is equal to 3. And so we're accessing 3 because we passed the array. Since we passed the array to the method call in the main frame earlier in the code, it now has access to that spot on the heap, and so it can still access everything from the heap itself. So it's accessing the length value for the array. And so it's accessing it, seeing that it's 4 minus 1 is 3. And so obviously the test fails, meaning that we have to go to the else condition lower down in the code. So in the else we have our return statement. Our return statement is fairly straightforward. We are taking a position, or we're taking an index from the array associated with the position that was passed to it, and we are adding it to a recursive call. And so, just for so the sake of space, I just called that method. And so, like the sum above it, this is not completely finished because we are still having to wait for another method to finish before we can actually, finish this simple addition, right? And so we're returning, value, val's position plus a method. And so, we have another, double dash just to kind of like show that, this addition is not finished and it can't be finished yet. So what do? Well, we call the method, right? We increase position by 1. And so, we increase position by 1, we call another method, we add that back to the stack. So now we have 3 things set on the stack. And so here we do our simple test. We see the test for our base case. We see, hey, are we at the end of the array yet? It goes to it, it sees, okay, we're not. So we go back down to the else statement again. So again, we have now, we're accessing val's of position. Position was incremented by 1 from the last array call, or from the last method call. And so, inside this frame in the stack, position is equal to 1. So we are accessing the first index of the array, which is 7, and we're returning 7 plus the method, another method call. For that method call, we again increment position by 1. So now position is set to 2. And we're going back to the top as we have now made another call to the same method. And as you'll see, we now have 3 variables that are still waiting on data for them to actually return anything. We have the initial sum back in the mainframe that is still empty as nothing has been assigned to it. It's still waiting on the method that it called to finish, so it's waiting on that first sum array from position to finish processing so that it can actually be assigned a value. The first sum array from position, so the one 2 up from the blue arrow, that one is now waiting on the second one down, so the one above the blue arrow, to finish processing so it can increment that value to 1 so that it can return it back to the mainframe, so on and so forth. So now that we have 3 values that are just waiting for another method to finish. All right, so we do our base case, and yet again we find that 2 is not equal to 3. So we do the same thing as before. Now we have 4 values that are all waiting on some method to finish before they can actually finish processing themselves or finish being assigned or returned or whatever it is they need to do. And now we have return is for plus another method call. This method call being basically the same as last one's, except now the position is incremented by 1, so the position is now 3. So we now have the position equal to 3, and so we are going then back to the base case. Hey, what do you know? 3 is equal to 3. So now we can. So now, if if things are coded properly, then we can now begin to end the recursion and actually back our way up towards where we were before. So now that we get access to line 17, we just have to access the position, the certain index of the array that we need, which is equal to 9. And so now we can actually start to return values. So now we work our way back up the stack, to get to assign sum of value essentially. So what does this look like? Well, we keep, we're back to line 19. From line 19, we get to see that we can finally finish this, and we're finishing this from the 3rd sum array position that we created, the 3rd place in the stack. And so we have 4 plus blank. And so now we actually have a value for blank. The value is 9. We got 9 from the base case. And so 4 plus 9 is then going to be 13. And one thing you'll notice about this is that, like the for loop, when we did this iteratively, and as we're doing it now, we started with 0. However, when we're actually doing the summation, with the recursion, we're doing it backwards. So when we did it iteratively, we did 1 plus 7, we did 8 plus 4, and then we did 12 plus 9. When we're doing it with the recursion in this fashion, we're essentially doing that summation the opposite direction. So we take 9, and we add that to 4 to get 13, plus 7 to get 20, and then plus 1 to get 21. So it gets the same results, but the addition is now going in the opposite direction because that's how the stack is kind of like working its way backwards. So now we're still at line 19. Also, I forgot to mention, now that we finished returning a value from this method, we get to pop it from the stack. And so it's also then no longer accessible, this frame, to anything else in the code. So Java will garbage collect it, and it will basically be removed entirely. So now that that's gone, oh, that's the wrong way. So now that that 4th frame is gone, we then get to go to the next one. So 7 plus 13, the 13 being the value that the 3rd frame returns, so on and so forth, 21 plus 1. And then finally, when we get back to the main frame of the stack, we get to assign 21 to the sum. Then, of course, we print it, and then there we go. Any questions about kind of like this general idea of recursion? Yes?
Could you explain what the benefit of this technique is over the for loop, or what situation it might be more optimal?
Okay, so yeah, again, you can't really see like the benefits of doing this as well, through this example, because what this example does is it just kind of like, it basically mimics, the iteration. Like this is basically a one-to-one iteration, mimic of iteration. So, what if, how would I make this better, and how would I make this so it actually like, shows how recursion works better. So one way that I can think of, and this definitely would work better with a larger array, but what if we kind of like kept the same general outline, but what if we changed? What if like we also then changed the array that we're passing? So basically what if we get rid of, and so this can be a little bit of a thought experiment, because, so basically we get rid of the int position value, and we just have the array. And so what we're going to basically be doing is, we're going to basically be cutting this array in half every single time we do the recursion, right? And so, and then, of course, because we're getting rid of the position, we have to change our base case. So let's just make our base case something like when the array is of size 1 or 2, right? And so, when it's of size 1 or 2, we just add the two values together. But if it's not, what we do is we take the array and we cut it in half. And so we cut the array in half. So let's say we have an array of size 10. We cut it in half. We have 2 5s, right? So then what we can then do is we can do the same recursion on both of these 5s, right? And actually, I guess, OK, let me actually get out. Let's actually like, okay, let's just actually like mull this out a bit. Doing fairly good on time, so. Okay, MS Paint, the best teaching tool out there. Okay, so basically, like, say we have, our array here, and one of the things we're going to be doing is we're then going to divide it into, 2 halves. So, and we're going to, call the recursion on both of them. So basically, what we're going to be doing is say we have, in our recursive step is basically taking this array and splitting it in half, right? So then we have 2 smaller sections. Then we get to call the recursion again. So then we have 2 smaller sections. So if this is, let's say this is, size 10, this would be, size 5, size 5. One of these would be, size 3. Size 2. And then we can just copy this over for the next one. And then, the size 2 one meets our base condition, so we can end it there, but the size 3 one does not. So we need to make, an additional section. I'll just copy an additional division. So we have now a size 2, and then we have, it has to be big enough for text. So size 1. Okay, and so so basically it's kind of like this is an example. I'm not sure if it's necessarily the best one, but the idea is like one of the things we can do with recursion is we can just divide things up very nicely. So we can kind of like change how we approach a problem altogether. So if we were to like actually process this, the size 2 one, those two would sum together, and then it would take the recursive step backwards, and then it will sum it with this one. So then 3 things are being summed here. But also one of the things you'll notice is that this is kind of like a tree, right? We're breaking this down. We have different branches, and it's kind of it's very tree-like, and so that's one of the really good things about recursion if you do things, and trees are kind of like a data structure type thing in, programming. And so, going through trees and like processing things as trees, actually let me make this bigger for you guys. Can I do that? Not really. Cool. All right. So, see how this, we start with 10, we kind of subdivide it. So we have 5, 2 5s, 3, 3 2, 3 2, and so we kind of like these like two, we have 5, of these leave type things, right? Or we have 6 of these leave type things. We have the 2, the 1, the 2, the 2, the 1, the 2. And so then we can, we work our way back up the tree now. We add them together. So then we have 3 things added together here, 2 things added together here, 5 things added together here, 5 things added together here. And then, all 10 things added together at the top. So basically what we can, one of the things that recursion does really well is doing this like sort of subdividing. And so you can also do other things like it's easier to call like, do method calls and objects and things. Most of this, you'll, for right now, you probably won't, appreciate everything recursion can do. But definitely when you get to like higher levels, you'll start to see that, okay, this actually has like, a lot of potential to it. So does that kind of, cool. Any other questions? Hopefully I didn't cause more confusion than I worked to answer. Anyone? All right, cool. Did I press the right button? There we go. All right. So yeah, we finally get to the print statement, and then we can return the sum value. Okay. But we also are going to, recursion also has a few hazards to it. One of the things I mentioned earlier is, what if our base case didn't fire off, and then we have like infinite recursion going on forever, right? So but another issue could be, what we'll find in example too large. So, we have like, another integer array of values. It's just going to be, casual 10 million things, right? Not a big deal. One of the things, of course, like, if you're just looking in the code, you'll find that, it might look a bit weird because we aren't assigning anything to any of the values. It's just a giant empty array. But we're not going to worry about that right now, okay? And so, we're going to be doing similar steps. This is kind of like the same. This is basically all the same code as the same method. And so we're going to do like, similar steps to what we did before. And so, I'm just going to like speed this up a little bit, and we're going to do it at, double speed. And I promise at the end of this, there's going to be a joke so bad and so first that you will learn to appreciate the puns in your recitations. So. All right, so we're gonna, this is kind of like seems reasonable. We do our initial call. We have, this one, this one frame added on. Okay, we're gonna go ahead and double the frames for the recursion. So now, we've got 2 frames. Still pretty reasonable. Okay, going up to, there should be 4 of them there. I think that was a mistake on my end. So we should have had 4 frames there. Only 3, but let's. I'm pretty sure I fixed it later. Okay, so 8 of 10 million, was it like we need 25 more slides for this or something? Okay, so this is starting to get, it's starting to get a lot, We have 16 of 10 million, this is starting to become like a little bit cluttered. I had to, move it over, I had to, give it a little bit more space to work with. Okay, so it kind of seems that our stack is beginning to overflow the space on the screen. Yeah, it's really, it's really overflowing it, right? But it's a Stack Overflow error. Anyway, now you will appreciate your recitation jokes. You're welcome. So, when a method, when there are so many method calls added to the stack that it exceeds the memory space allocated to it, the program can't continue because it can't add anything more to the stack. And so, in this case, we're adding so much, we're adding so many method calls to the stack that it basically can't handle it anymore, and so it's going to crash. It's going to, throw, it's going to be a runtime exception. It's going to be a Stack Overflow error. When you're making the code and you're coding it, as you can kind of see, do I have a big picture of the example code? I don't think so. No. Basically, if you look at the code, everything compiles. Like, it's all there. There's no like, error message shown to you when you're, when you have the code in Eclipse. There's no like red spot. There's like nothing. The issue isn't, the code itself. In theory, if we give it enough memory, the code can run. The issue comes that we just don't have enough memory assigned to it currently for it to do this. Does that kind of make sense? We don't have enough memory to do 10 million recursive calls, believe it or not. So, let's look at kind of like iteration versus recursion. So, the iterative program is kind of like more self-contained. It kind of like reuses the same sort of like, if you were to think of the darker green as a frame, which it's not, but if you were to, it's kind of self-contained in that. It's constantly reusing the same section. Whereas, with the recursive calls, they keep adding to the stack, so you have that potential for a stack overflow that's just not there in iterative. Okay? And again, why use recursion? Well, like I mentioned before, it's easier to subdivide. It can make the code a bit more readable. As you'll see with like example 2 and example 2 large, one of the things, it's basically just sum is equal to one method call. Of course, you can also do that and have the method call be an iterative loop, and that could also work. But in general, you could also make it so parts of the code are a little bit more readable and a little bit more clear. And there are problems that are easier solved with recursion than there are just doing an iterative method. Of course, like when I take a iterative problem, such as going through an array and adding up all the values, and translate that over to recursion, there's going to be it's going to have like a bit of a headache, right? It's not going to show the full potential of it. So, yeah, that's kind of in general the slides. Are there any kind of like questions about this topic in general? Anything you guys want me to maybe go back on? Maybe try to clear up a bit more. Do you guys feel good? Okay, so I'll leave it up to you guys. We can either get out early or we can learn about kind of like a special type of recursion. Up to you guys. Well, yeah. If anyone's interested, I'll just stand up here and keep talking. But yeah, feel free to leave at this point, but we're going to just kind of talk about like a more conceptual version of recursion if anyone's left. So basically, to kind of continue onwards, one thing that we can do is something called tail order recursion. So if you remember from the slides, we have, back way up here, we kind of have like all these variables waiting for a single. All these additions are waiting for a single value, right? And so they're waiting for one value to continue the summation. So then, the idea that we could potentially do is, what if we passed the continued sum as a method parameter, right? So we have, int sum, and this is continuing to add, right? And so this can be like a bit more recursively, more like the iterative way, where it's going from the front of the array to the back of the array. It's going from the index 0 to the index 4. So, we're taking, we're starting at 0, we're going at, and I'll just use this example, continuing to kind of use this sort of image to kind of help you visualize this. But, we're starting at 0. We take the 0, we add it to 7. Or we take the index of 0, which is 1, we add it to 7, we get 8, right? So we have 8, and so we then pass that along. So we've already done the summation, and we're passing the summation as a variable to the next parameter in the recursion. So basically, we just have return, and then we have the method call, right? And so we then have, in the next method, it's still waiting, in theory, for it to continue. Actually, I'm just going to go ahead and open or get Eclipse up, and we can, let's just let's actually do this. So what if we, we kept these 3 variables, but we also had, int sum, right? And the sum's going to initially be 0. I think that's visible enough. Let's get the console window a little bit bigger. And so all right, so we have we have the sum is equal to sum from array, and we're adding this on as an extra parameter. And so we can kind of get rid of this addition here because we no longer need it. I'm going to go and cut it. So what we can do now is we can do sum. We can just return sum plus val's position. And then we can change this to return sum, right? And so basically what we're now going through and doing is we're taking sum array from position. We now gave it an extra parameter. And so now we're doing all the summation with the recursive calls, right? So if we, thinking back at this array, we have the one, and let's just run it to make sure this is working right. Oh, that is a. Oh, I forgot. I'll just need to do sum plus val's position. So I bumped the HDMI cord. Lovely. Up, there we go. Nice. Okay. Yeah. If you have it coded correctly, we get 21, right? Same value, except now we're doing this in a slightly different way, right? And so now the idea of this is that we have basically a return statement, which gives us another method call, which gives us another method call, and gives it another method call. So the return statement isn't waiting any longer for the sum to continue, right? It doesn't need to continue to add before it can return a value, right? So in theory, it's almost like we have a return call followed by a return call followed by a return call, right? Can you guys kind of visualize that? I can do a fancy MS Paint diagram if you need to. Do you guys have the idea of that? I just want to make sure it's kind of I'm doing this very abstractly, so okay. Yeah, so essentially we have we have a return call followed by a return call followed by a return call. We don't really need anything else in any of those, in any of the middle recursive or in any of the middle frames. We don't need anything else. So the question is, could we just get rid of them? And instead of having a bunch of just return calls following one another, could we just have it return once to the main thing? And so this is kind of the idea of tail recursion. It's basically we're getting rid of all the different recursive steps, and we're making it so it just goes back to the start. And so this, again, this is a purely conceptual thing, because fun fact, this doesn't work in Java. So in other programming languages it will work. I can't remember. I have a few example ones, but I can't remember those off the top of my head right now. If we got to this, I wasn't actually expecting to have as much time as I was. But yeah, in theory, in other programming languages, you could just have a recursive call like this that is equal to that you have an integer array that's equal to 10 million, and that actually processes without any fear of Stack Overflow, because it keeps getting rid of all the extra recursive calls that just have a return, just are returning a value, right? And so that's kind of the main idea of that. One extra fun little thing to think about in your coding careers. Maybe it will come into use, maybe it won't, but I think it's interesting. All right, so yeah, I'm going to end it there. Hope you guys enjoyed or thought it was at least reasonable. Yeah, have a good rest of your days. I'll be down here if you also want to ask me any questions or anything else. So.